So a chemical reaction is something that occurs when you change the components of a substance. For example, look at this case. So we have two hydrogen atoms. So in total, we're going to have 4 hydrogen atoms in gas state. This is in gas state, okay? And we have oxygen. This is molecular oxygen. We have 2 oxygen atoms. In what state is this? Is this a molecule? Gas. Yes, that is right. This means the state. Okay, this is a state. The state of matter, right? Okay, so if you combine these 2 molecules, they will react, okay? And they will form a new molecule with a different behavior. And this is what we call in science chemical reactions. So these chemical reactions can be represented by something that is called chemical equations. Really well. So question, how can we represent chemical reactions? Okay, so look, in a chemical equation, we find different parts, right? So you can find, for example, a subscript that is this small number that is to an atom, right? To an element, in this case, the hydrogen atom. You can find okay, this represents the moles, no? We can find the coefficients, right? And they will be indicating that we have. In this case, we also have one part of the equation that is going to be called reactants. And the reactants, as its name says, will be reacting. Okay, they will react. Okay, that's what this word means. Okay, and then we have an arrow, and this arrow will indicate they will have a reaction. So this arrow is called the reaction arrow. Okay, that will lead us to have products. In this case, I want to ask you something. What is the name for this molecule? We have a water molecule, but a question, how many molecules of water do we have? 2 water molecules, right? So in a molecular way, we can say that we will have an oxygen, and the oxygen is negatively partially charged, and we have 2 hydrogen atoms, right? And then we will have another molecule of water. It can be something like this, not that perfect, but I guess it's something similar, right? Okay, in what state is this molecule? Remember that the state is between parentheses. This is also gas state. And the question is, in what state is this molecule? What are the states of matter? States of matter are 3, right? Okay, they are 4. The basic states of matter are 5 in fact. So we have solid, gas. We also have plasma, the Bose, condensate. So this is going to be liquid state. Okay, so we have seen that the molecular composition, that is this one, has changed, right? Because in this case, we have 2 water molecules. Here we have 4 hydrogen atoms, right? In gas state, we have 2 oxygen atoms, right? And they were in gas state, but when you combine them, they will form 2 water molecules, and those molecules will be in liquid state. All right, and this is what in chemistry we call chemical formula. Okay, so when you find these expressions like this one, like for example, CO2, that is carbon dioxide, this is called chemical formula. Okay, so the objective for this class is to assess what the student understands about redox reactions, right? So redox reactions in our daily life. So you see the importance of redox reactions in our lives. We can have energy production, right? So redox reactions, this type of reactions are going to be involved in electrochemical conversion, like also the electrocatalysis, right? uh, the electrochemical storage when you need to store energy, right? So redox takes place when it flows through batteries, right? And also in solar panels, right? So when we use renewable electricity production, it will require this type of chemical reactions. I mean, renewable means that you can renew something, you can make it new again. So it sounds weird, but okay, that's like the idea. Renewable. You can reuse something because it's renewed. As we have said, redox reactions are really important, right? So, for example, in combustion processes, we normally have redox reactions. Also, as I told you, in biological processes, for example, in the production of in the production of photosynthesis. You know what is photosynthesis now? Photosynthesis. You're going to use glucose. That this is a glucose molecule, CH, C6H12O6 plus CO2 is going to produce a carbon dioxide plus water, right? So by using the glucose, look at it. We're in oxygen, molecular oxygen. We produce all the compounds that are carbon dioxide and water. Okay. All right, one of the tips that I provide to my students is basically that when you have a pure substance, in this case, this can be called pure substance because we only have oxygens here. When there is a pure substance in one part of the equation, this pure substance is going to be a redox reaction. Why? Because there is a pure substance. When you find pure substances, all right, that's going to be a redox reaction for sure. As you can see, this, for example, um, the oxygen, in this case, the oxygen, that is this part of the equation that is in the reactants, is going to gain electrons, right? So the oxygen will gain electrons and hydrogens, is this part. So in this process is gaining electrons, okay? But in the other case, the part of the glucose, that is this other molecule, it will be losing electrons. Okay, so what I can tell you is that when they form compounds, they have to use their oxidation numbers, right? So, for example, in this case, oxygen is going to have a 0 as oxidation number, right? Because it's a pure substance, it's not forming compounds, right? But when oxygen, for example, is combined with a hydrogen atom, and the hydrogen atom normally is going to be +1 or -1, right? So we're going to say oxygen when this is in a compound, you can say that oxygen is -2, right? So in this case, the oxygen is 0 and it will be gaining electrons because its oxidation number is -2. Got it? I don't want to go deeper, right? I don't want to go into this topic yet, right? Because I have some slides that will talk about that. But what I can tell you is that, okay, so this is a simple example, right? But this is what happens, right? I'm not gonna go into numbers yet. Just try to be conformed with the idea that they will lose and gain electrons, right? So that's the best you can do for now, at least in this slide. Um, in this case, for example, the glucose is going to be losing electrons, right? And as it loses electrons in hydrogens, it will be oxidized. Let me give you an example about this. Let me exemplify this case, right? So redox means reduction and oxidation. Let's go to the next slide. So also, the redox reaction is going to have place in metal corrosion, right? So when you have there is a metal that is rusting, or there is a redox reaction taking place. Okay, so look, this is what basically happened here. In the previous equation, we had this expression, H12O6. You see this part, we're gonna invert it. So this was written this way. Something like this, right? But if you invert it, right? If you invert this equation, if you invert it, you're going to find the opposite, right? So that for example, the carbon dioxide is going to reduce, right? And the water molecules are going to oxidize, right? So, all right, all right, that equation just to show you that we can represent this redox reaction this way. Redox reaction in a voltaic cell is an electrochemical cell that uses a redox reaction to produce electrical energy. So as I had told you, we can use, for example, zinc, right? Zinc and copper, right? So they will gain and lose electrons. This is the equation that takes place in this case. So let me explain you this equation. What we're going to have here is the copper sulfate. The name for this whole molecule is called copper sulfate. Okay, so zinc is going to be in solid, sorry. And copper is going to lose because we have these two positive charges. And remember that in the atom, this is the atom, we have different charges, right? What is the charge that we have inside? Is a positive charge, right? We're talking about subatomic particles, right? These are called subatomic particles, the particles. So we have plus means proton, right? Negative, what does it mean negative? Electron, really well. And the electron is normally spinning around the nucleus. So the electron is this, okay? The proton is bigger than the electron, right? Here, I just made a mistake because I drew the electron as if it were bigger than the proton, but it's not that way, right? And a non-charged particle that is in the center, also conforming what we call the nucleus. The nucleus. Nucleus, and the electron will be spinning around the nucleus. What is the name for that subatomic particle? That is right, neutron. Okay? When I say that we have two protons, right? Sorry, we have two positive charges, right? It's the same, right? This is what I mean. Pay attention. Look, I have. Oh, and I used to have two electrons also, right? But the electrons, they have gone. And that is why I will say that I will just have two protons. So this is what this means. It's like an explanation, right? So a question. In this case, the copper atom lost or gained electrons. That means that the copper atom lost negative charges. That is what that means. Okay. So look, the copper has lost two electrons, right? In this case, the zinc, the same. Look, what I will do is the next thing. So I will say that there is going to be a half reaction. And the half reaction stays, we're gonna draw element by element, right? Element per element. So zinc, that is this one, in solid. What happened with zinc? So in this case, it lost the electrons, right? Pay attention. Look, if I need to balance that thing that took place here, right? What do I have to add? How many electrons do I have to add to balance this part? Okay. Okay, now do the same, but with the other one. So come on, do the same, please. Copper. So I will write copper and it lost two electrons, right? What happened with copper after? That is right. Copper is in solution. Right, so copper is gonna be in solid here. Where do I add the electrons? In the first copper, really well. Come on, do it. Okay, and what is the name for this? What is the name for this process? This is half reaction, right? Okay, so I will give you a clue, right? So when you find the electrons, to the right, in this case, is oxidized because the oxidation number has increased. We put two electrons, it has increased. It's oxidized, right? But in this case, the oxidation number increased or decreased. Okay, and that's what we called because the electrons went to this side of the equation, right? You don't need to understand this fully for now, okay? I will give you more examples and you will comprehend it better. But that's just like a starting point, right? There is another hint that is when you find the electrons in the right part, it is oxidized. So in this case, the copper is going to be the reduced substance. It's reduced. Okay. And this is a reaction between the copper sulfate. This is called. Look, in the periodic table, I'm going to ask you to use the periodic table, okay? And this arrow indicates the electronegativity, right? Explaining that, right? Okay, so look at it. This is the electronegativity, right? But look, also we have the oxidation trend, right? This is what we call the oxidation trend. That is the tendency of the numbers to be oxidized, right? So how do we understand this? What is the oxidation number for noble gases? Because they are gonna have 8. So that means that they are stable. Okay, they are like the perfect guy. Okay, because they are in the group number 8 or 18 is the same. Okay, so they don't need valence electrons to be complete. All right, but look at this. Look at this. At these elements that are in the previous group, in the group number 7. Okay, how many valence electrons do they have? 7, that is right. We have 7 because they have 7 valence electrons. Okay, because they are, okay, question, are they stable or not? No, they are reactive, no? Okay, because they are in group, what is the group that they are in? That is right. So that's why we say that their oxidation number is -1. Okay, really well. The same, for example, in this case, we find oxygen. Look, oxygen. Oxygen has, how many valence electrons does oxygen have? 6, because it's in the group number 6 valence electrons. I hope you're taking notes. 6 valence electrons. Are they stable or reactive? Or 16, really well. And they, how many valence electrons will they need? And that is why in your periodic table, I want that you write this. -2, write this in your periodic table with red color or something like a marker, something you cannot erase. Normally, this, all right, what this indicates is that normally these atoms that are here, the elements that are in this first group, are gonna be donating electrons to these ones that are in the group number 7 to complete 8 valence electrons. Look at it. The ones that are in the group number 1, right? How many valence electrons do they have? One valence electron, no? So it's easier for them to donate or to give away their electrons to these ones that are in this group to complete 8 valence electrons. That is why we say that they are +1, sorry, because they are giving electrons. Instantaneously, they are losing electrons, right? So, for example, that is why hydrogen, the oxidation state for hydrogen is +1. You see? Because it's giving away one electron. And for the halogens is -1. For example, for fluorine or chlorine or bromine is -1. I need that you explain me why in the second group we have as oxidation number +2. They are giving negative charges, you see? And that's why they become into positive. So in this case, the oxidation state for the elements that are here is -3, right? -3. Can you give me an example of an element that has -3 as oxidation number? So do a nitrogen. What is the oxidation number for nitrogen? So full phrase. Nitrogen has an oxidation number of -3. All right, and I have an important question for you. Why the carbon can donate or give or obtain 4? Because he's in the group number 4, right? So he can obtain 4, or he can donate 4. In fact, it will complete the 8 valence electrons. In this case, we have zinc, right? In zinc, what is the oxidation number for zinc? Sorry. Remember that there is something that we call when we have pure substance, we only use oxidation numbers when we are forming molecules. But when the element is in pure substance, for example, if you have zinc, the oxidation number is 0 because it's not forming molecules, okay? Or you don't need to gain or to lose electrons to complete 8 valence electrons because you are alone, right? You're not interested in forming 8 valence electrons. That's what it means. What is the oxidation number for oxygen? 6 oxygen atoms. Pure substance is 0, okay? For hydrogen, when it's alone, 0, okay? But if I say, okay, if I say for chlorine, what is the oxidation number when it's alone? 0, okay? If I say 3 chlorine atoms, as is pure substance, its oxidation number is gonna be 0, okay? When is a pure substance? You know what is the difference between a pure substance and a compound, no? This is really easy. So if I take, for example, hydrogen, 2 hydrogen atoms and 1 oxygen atom, this is called compound, right? Different elements. That it? Three oxygen atoms. What is this? Molecule A is a pure substance really well. If you have, for example, carbon dioxide is a compound or is that a pure substance? Excellent, it's a compound really well. And if you have carbon with carbon, it's pure. That is right, pure substance. Because we only have one element, that is carbon. Is carbon here, carbon here. Not in amount, but in nature, right? That is a difference, okay? Look, what is a number that you find in the subscript here? It's an imaginary one. So you multiply -2 times 1 equals -2, right? What is the oxidation number for magnesium to be this molecule stable? All right, so let's verify. So +2, all right, so +2 times an imaginary one, +2. Yes or not? It's 2, no? So 2 minus 2 equals 0. Go and check what is the oxidation number for magnesium. So does it make sense? So look, chemistry is that perfect. So look at it. I will illustrate scale to comprehend better what is reducing, what is oxidizing, what is oxidized. So look, this is a scale. So the scale goes this way. So let's suppose that we have here -7. And here we have, okay? You know what is that scale? All right, that is a reduction in oxidation scale. Right? So let's suppose that we have like -7, -6, -5, -4, -3, -2, -1. Here we have this, the famous 0. And we have here like +1, +2, +3, +4, +5, +6, and finally we have +7. And this is the oxidation scale. Okay? So look, if we move from this point to this point, what are we doing? Oxidizing or reducing? Really well, because this is the oxidation scale, no? But if we do the opposite, if we run from this point to this other point, we are excellent, really well. Copy this scale, please. All right, so you understood? So look, let's take this concept to this case. You had said that this was like 0, okay? the same 0 because it's pure substance? Yes or not? This was -2 and this was +2, right? Question. Magnesium went from 0 to +2. Did magnesium oxidize or reduced? And this is what we're going to call the oxidized substance. Do the same exercise with oxygen, please. From 0 to -2. Reduced substance. Okay? When magnesium is the oxidized substance, right? It's gonna be, when magnesium is oxidized, it will be, by the way, the reducing agent. Because when it oxidizes, at the same time, it reduces, okay? And in this case, what is oxygen? Oxidizing agent. Do it, agent. Okay. Do me a favor, please. Identify the oxidized substance and the reduced substance, then the oxidizing agent and the reducing agent. My advice is try to first start with the pure substances because they are the easiest. Continue, please. What can you do? Remember, with hydrogen, what is the oxidation number for hydrogen normally? What do you do next? So multiply them, please. All right, so tell me, how much is the result? 1 times 4 equals 4. This 1 times 4 equals 4. Oxidation number for carbon, what is? If we have +4, what do we need in carbon? It's -4. We can play with this oxidation number. Oxidation number for hydrogen, we already know that it's +1. For carbon, it can be -4. Continue. And for oxygen, what is the oxidation number for oxygen? It's forming a molecule, right? And -2 times 2, -4. So what do we need in oxygen here? +4. All right. Hydrogen was +1, so 1 times 2 equals +2. And the oxygen is going to be -2. Okay. What is the reduced substance here? Reduced substance, really well. Oxygen. Carbon is going to be reduced or oxidized. Carbon went from -4 to +4. Is reduced or oxidized. In the scale of the oxidation, we had from -7 to +7, no? Increases, it oxidizes. If it decreases, it reduces, right? In this case, it went from -4 to +4, is oxidized. Okay, so question, what is the reducing agent and what is the oxidizing agent? Is this redox, yes or not? Is there any pure substance in one of the parts? It's not redox. And this one is redox. Excellent. And this, it is. And that other one, that is right. Okay.